Swayam Prabha. Digital India. Educated India.
Okay, we'll welcome everyone. We'll continue with our study of optimization. I had some questions from the previous class which I want to address here. Some of you are asking me about the difference between what is a sufficient condition and a necessary condition. So let us just recall this. We had concluded that if x star is a local minimum of an optimization problem like this, where you have a you are minimizing a function f x over an open set S, okay, then it has and if x star is a local minimum of this optimization problem, then it has to be that the derivative of f at x star or the gradient of f at x star, they must be equal to 0. This has to hold. So this is what we call a necessary condition. Okay, this means that if x star is a solution, then it must satisfy this. Now, we also got a stronger necessary condition which said that the Hessian of f at x star must be positive semi-definite. Okay. So, the condition is written here in blue. So, it said that if x star is a local solution, then the Hessian of f evaluated at x star must be positive semi-definite. This is also a necessary condition. So, if x star is a local minimum, then the Hessian must be positive semi-definite. Okay, this is what this condition says. There is a condition which goes in the opposite direction, which says that if such and such condition is satisfied, then x star is a local minimum. That is what we mean by a sufficient condition. So, that is what is written here in red. So, a sufficient condition for local minimum. So, suppose x star is a point in S, okay, and again we are in the same setting. S is an open set, f is a twice differentiable function, and suppose we have that the gradient is of f at x star is equal to 0, and moreover the Hessian is positive definite, okay, which means that V transpose Hessian times V is strictly greater than 0 for all V not equal to 0, right. So, if the Hessian is positive definite, then x star must be a local minimum. Okay. So, this guarantees that x star is a local minimum, okay. But every local minimum may not satisfy this. There are local minima that violate this, which are that violate this, but they must satisfy surely the other necessary conditions, which means that the derivative should be equal to 0 and the Hessian should be positive semi-definite. Okay. Also, a quick outline of how the proof for this sufficient condition for local minimum would work. Remember, by Taylor's theorem, we had argued this in this equation here, f of x star plus delta h, where delta is some small positive quantity, h is a direction in Rn. So, f of x star plus delta h can be written in this sort of form: f of x star plus half delta square h transpose the Hessian of f at x star h plus something that is small o of delta square. Now, how did we get here? We got here by using that the first order term, the linear term in h, actually is 0 because the gradient is equal to 0. Right? The gradient of f at x star is equal to 0. So, this term vanished and you are left with only this term. Now, if you look at the difference between the left hand side and the right hand side, okay, if you look at the difference between the left hand side and the right hand side, let me, so if you look at the difference f of x star plus delta h minus f of x star, this quantity is equal to half of delta square h transpose del square f at x star h plus something that's small o of delta square. So, you have this, you look at this difference. Now, we know that when delta is small enough, what must happen? See, remember, we are arguing in the opposite direction. We now we want to say that if the Hessian is positive definite, then x star must be a local minimum. Okay. So, which means that we want to say that when delta is small enough, this quantity, the quantity on your left hand side here, the quantity on your left hand side must be greater than equal to 0 for delta small a. Okay. So, the way to see that is to just simply take delta square common here. You have left with then half H transpose this plus this quantity, which is small o of delta square divided by delta square. Okay, this is true for all. So, for delta positive and small enough. Now, we know that when h is not equal to 0, when h is not equal to 0, this quantity, this underlined term, this term is strictly positive. Why? Because the Hessian at x star is positive definite. So, this is strictly positive for h not equal to 0. This is because the Hessian is positive definite. Now, because the Hessian is positive definite, this term becomes strictly positive. And what can we say about this other term, the term that I have circled? It's a term because the numerator is small o of delta square. I have divided that by delta square. What that means is it's a quantity. Small o of delta square is a quantity that upon dividing by delta square also goes to 0, right. So, small o of delta square divided by delta square goes to 0 as delta goes to 0. So, as delta becomes small, this quantity will become eventually smaller in magnitude than the first term. It goes to 0, so eventually it has to become smaller in magnitude than the first term. If whether this term is positive or negative does not matter to us. Eventually, in magnitude, it is going to become smaller than the first term. So, consequently, whatever is there in the bracket here is going to add up to something positive for delta small enough, right. So, this is this bracket for delta small enough, this bracket is positive, and outside I have a delta square which is also positive. Right. So, in short, what have we got? We've got that, well, if as a consequence, we've got that this difference is definitely greater than, equal to 0, which means that okay. So, that gives you that, which implies that x star is a local minimum. Okay. So, this is guaranteeing that x star is a local minimum. Okay, now let us do a couple of applications of this. First set of applications are going to be where it is evident that the optimization problem is actually an optimization over an open set. In the second case, what's going to happen is that it is not very evident that it is an optimization over an open set. It has to be mathematically transformed in that sort of way. Okay, and that will also lead us to our next class of optimization problems. Okay. So, the first category is this problem of what is called least squares regression. So, the problem in this kind of the question in this kind of problem is that you have a bunch of uh, you have a bunch of inputs, or you can say independent variables, which affect an output, and we want to infer a relation between input and output. And the relation is not always exact. We don't, the inputs and outputs are related to each other possibly in a noisy fashion, but we do not have a model for the noise. We do not have, there are probably many other unmodeled things, elements in the problem which are affecting the output. So, consequently, we do not have a perfect relation. What we want to infer is a relationship that will be good enough for predictive purposes. So, it may not be good, it's not necessarily good for, it's not enough that we that the relationship is matches very well on the data that we have, but rather our goal is actually that it should perform well on unseen data, in order to and give us good predictions on unseen data. So, I will explain this with an example. Suppose we are talking of, say, price of a used car. Okay, just as an example. So, price of a used car. Now, used cars come in all kinds of varieties. But we can think that maybe the price of the used car depends on a few input variables, such as, for example, the age of the car, such as the brand or make of the car. It depends on whether it is a petrol or diesel variant. It depends on the condition of the car. Depends on the number of kilometers it has run, what has been its running, etc. Okay. So, these are, in the language of machine learning, are what are called features. Features are what I was calling input variables. So, these are what are called features, and the price of the used car is what we want to infer from it. So, what we want to infer using the features. So, if I give the goal is that I give you a sample car which has a sample used car which has all these features. It has a certain age, I tell you its brand, I tell you whether it's a petrol or a diesel car, I tell you its condition, tell you the number of kilometers it has run, and I want you to predict what the price is going to be. Okay, at what price will this sell in the market? This is the problem. And now, of course, you cannot do this in without any data. So, I will give you some previous data. Okay. So, I will give you previous data points. Okay. Now, previous data points, what do these previous data points correspond to? They give you a list of features, they give you values for features, and they tell you the price. Okay. And the price at which the car sold. Okay. This price is what we call a label. So, you are previously given, you are given some previous values of the features, and you are given also the values of labels corresponding to that. Okay. And now, what the goal is that using all this data, you come up with some way, some predictor for a new sample. New sample does not mean a brand new car, a new sample of an old car, of a used car, okay, an unseen sample, which possibly has a different values of features, and use that to predict the price. Okay. This sort of problem is a sort of a basic problem in machine learning. Now, what we need, let's introduce a bit of notation here. These features, I will let's denote. Features are going to be denoted as in the following way. So, I have suppose so I have suppose n features. N features include things like this, and these I will assume they take values in a continuous space. So, here these either or type features or brand type features which are discrete. Let me not let's ignore them for the moment. Let's assume that these are n features taking values in the continuous space. So, this could be age of the car, some way of measuring condition, the number of kilometers it has run, and so on. Okay. So, these are features that n features that are real valued. Each of them is a real number. So, and I am going to give you m samples or data points. So, the way this is we will denote this, since there are n features. So, what we will do is we will stack all of them into a vector. So, for the ith sample, the values of the features that you have, let us denote them in this sort of way, a I of 1 dot dot dot, so a I of 2 dot 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 a I of n. Okay, this becomes a row vector like this. Okay. The column vector like this, a I will just be the column vector formed by these. This is a column vector. The price or the label that we have got for in the ith sample is denoted bi, and this is also a real number. So, label now what one typically has also in addition to this is a bias feature. I will ignore that for the moment, but so for simplicity, just let us look at this sort of question. You have previous data points here. This is my feature space, the space in which my AIs take their values. So, I have a say A1 here and a corresponding B1 here. I have an A2 here, A2 suppose, and a B2 and the A3 and a B3, B3, etc. And so, you get these sort of, you have these, okay, you have these m samples. Okay. Does everyone understand this? There are m samples, that is the m is the number of dots that I have here like this of this kind, n is the length of the feature vector. Okay. Now, what I would like to do is somehow come up for a new unseen point. So, here is a new point in the feature space which I have never seen before. I would like to know what should be the right value of the price or the label for this, correct. So, if I want to do this kind of prediction, what I need to do is build a model using the data that I have. Okay. And so, what we will posit is we will hope for a linear relationship. Okay, we will let us posit it in this sort of way. Let us posit that bi depends on AI in a linear fashion. Now, what this means is, so let's suppose that you compare the true value AI, true value Bi, with the value of a linear function of the features, which is denoted like this: AI transpose X. Okay. AI transpose X. So, this is a linear function on linear function of the features. So, the coefficients here X are this vector x1 till xn. These coefficients define, as I vary the coefficients, I will get a different value for AI transpose X, and I am hoping to get coefficients in such a way that when I these coefficients in such a way that when I input a new set of features here, unseen set of features, it will give me a good approximation or a good prediction for the price or the label. All right. Now, the trouble is, if you look at the sort of figure that I drew here, data the way it is, because there are so many unmodeled elements, there is clearly need not really be a linear relationship between the label and the feature. Okay. So, what one tries to do is, then you think of a cost function or a loss function. We try to look at the mismatch or look at the residue like this. Look at the residue like this, and we say, well, we would like to find an X such that these residues, as I goes from 1 till m, these residues are as low as possible. Okay. This is what's called the training problem. So, you try to find X's and thereby define this function, okay, define this linear function through those X's. So, you try to find X's so that this residue is as small as possible. So, a popular way of doing this is to simply write it like this. So, let us write A as this matrix. So, this puts together all the observed features of the m data points. Let me write B also as this column vector. These are the observed labels of the m data points. So, A is now a matrix in R m cross n, B is a vector in R m, okay. And because there need not really be a linear relationship, what we will try to do is find an X such that these residues are, the sum of these residues is minimized. Okay. So, now the residues can take any sort of sign, so it does not make sense to just simply add them. So, what we do, so you need to take a norm of them. So, let's take, so what I am taking here is I am taking the L2 norm, I am squaring the residues and summing all of this over the m sample. So, I am looking for an X in Rn. So, X belongs to Rn, remember, that minimizes this particular loss function. Okay. Another way of writing the same thing is to simply write that this is norm of this vector Ax minus b. The L2 norm of that vector is what we are minimizing. All right. Okay. So, what this problem does is it gives you the optimal set of the optimal x's. X's have different names. They are called regression coefficients in some language, in some communities. They are called in weights by some. What matters is basically they define for you once the optimal x has been found, once the x star, the optimal x. So, let us call that x star, the optimal solution. So, if once the optimal x star is found, in order to predict the price for an unseen sample, what I need to do for an unseen sample, say suppose if I find a new sample A tilde, what I need to do to predict the price for that is to simply do A tilde transpose x star. Okay, this is my prediction. This is the idea behind it. Yes? No. So different norms have different properties and different shapes. So, this goes for more and more into data science. I wasn't prepared to discuss it right now, but I'll give you a general idea. See, when you look at points like, when you get a bunch of data points like this, not all, some of them can also have what you can call outliers. So, a data point like this, which really is well out of the trend, right. So, the general hypothesis in this sort of work is that the data comprises of a trend plus a bit of noise, and we want to capture the trend, but not the noise. But there will occasionally be an outlier which comes because noise is random. There will occasionally be an outlier like this. And now, what that kind of outlier can do is that it can have an adverse effect on your choice of x star, because of the way you are training your algorithm. Right. So, on the way you have defined because of the way the x star has been found, that it can skew the choice of x star a little bit. So, that to the point where now the noise starts playing a bigger role than the trend. Now, as a consequence, what you would one way of getting rid of that is, instead of handpicking and saying that, well, this is an outlier and that is an outlier, you probably don't know what is an outlier to begin with. Instead of doing that, you try to look for a different loss metric itself. So, instead of the Euclidean norm, look for take a different norm. So, for example, you can take an LP norm. So, now you can raise all of these to the, instead of power 2, you can raise all of these to some power So, this is the LP norm. There are other types of loss functions that penalize large deviations much more than they penalize small deviations. Okay, so that you can choose one of them. So, this goes more and more deep into what you want, what the purpose of the study is, what the nature of the data is, and so on. But this is just a simple illustration to show that I wanted to show you.